Scientists are sure there is only one way to avoid a global energy crisis of the future: to create an alternative and inexhaustible source of energy. For example, learn to control the thermonuclear reaction, the very reaction that is constantly occurring on the Sun, making it generate an enormous amount of energy. After realizing in the first half of the 20th century what exact processes in the Sun generate power, scientists thought, what if we reproduce the energy of the luminary in the terrestrial conditions and seize the energy of thermonuclear synthesis?
We understand that since nature has provided us with such a possibility, humanity will always digest it, tame it, and find a way to use it for its own purposes.
So how did the scientists manage to replicate on Earth the processes that take place in the Sun, a huge glowing gas ball that exceeds the mass of our planet 333,000 times? It turned out that to light up a star, it is only necessary to borrow the principle of the thermonuclear reaction of the Sun. Slightly different operating elements were selected to achieve fusion in the terrestrial conditions.
On Earth, we have much more efficient fuel than the one available for the stars. We can even say that this is our advantage, the advantage of humanity before nature. Nature basically only has regular protons to start a nuclear reaction. We can make the fuel much more effective if we use deuterium and tritium.
Deuterium and tritium are isotopes of the lightest chemical element, hydrogen. Deuterium is a heavy, stable isotope, the nucleus of which consists of a proton and a neutron with a total mass of 2 atomic units. Tritium is a super heavy and radioactive isotope of hydrogen. Its nucleus consists of a proton and 2 neutrons with a total mass of 3 atomic units. As early as in the 1950s, scientists came to the conclusion that with these heavy isotopes of hydrogen, it is possible to perform a thermonuclear reaction. Deuterium and tritium can also be found in nature. Moreover, there are literally oceans of deuterium on our planet. This hydrogen isotope is found in seawater. The situation with tritium is a bit more complex. It is formed in small amounts in the upper layers of the atmosphere, upon collision of space particles with nitrogen atoms, for example.
Unfortunately, it is a rare material, and it has to be specifically created. Currently, it is mostly received as a byproduct of operation of heavy water reactors. On the other hand, it can be specifically and artificially created. There are certain process schemes for a thermonuclear reactor, where lithium is converted to tritium during neutron irradiation due to the course of reaction. This tritium is collected and provided as fuel for thermonuclear reactors.
For a successful thermonuclear reaction, the mixture of deuterium and tritium must be heated to ultra-high temperatures, 90 and even 180 million degrees Fahrenheit. This is several times more than the temperature of the solar core. This is the only way the nuclei of deuterium and tritium can accelerate and overcome Coulomb repulsion forces in the gas mixture of hydrogen isotopes, which is transformed into fully ionized plasma. This will allow the atoms to merge, forming a neutron and a helium core. As a result, the energy, equal to 17.6 mega-electron volts, will be emitted. However, before implementing this scenario, scientists had to solve a serious problem: figure out where and how to keep the incredibly hot plasma in order to prevent the thermonuclear reaction, both from going out and from destroying the reactor. In the Sun, the incredible gravity takes care of this problem, but it's impossible to recreate it on Earth. It would seem an insoluble task, but a way was found.
Plasma is an electrically conductive liquid, or a gas to be more precise. It behaves both like a liquid and like a gas. Therefore, it is natural to try and lock it inside a certain volume. But it is impossible to lock it that way. Plasma won't understand it. It will spread across the walls of the volume and go out. And that will be it. Accordingly, there should be a vessel of some kind that will hold the plasma. Magnetic field can be used as such a vessel, since the plasma obeys the laws of magnetic hydrodynamics and doesn't go beyond the limits creating the configuration of the magnetic field.
The idea of magnetic retention of plasma was suggested by future Nobel Prize winners Andrei Sakharov and Igor Tamm in 1950. 8 years later, the first experimental thermonuclear installation with a magnetic field trap was built in the Kurchatov Institute under the name tokamak. This word subsequently became an international neologism. Tokamak stands for the toroidal chamber with magnetic coils. It has the shape of a donut, a toroid scientifically speaking, with the coils wound around it to create a magnetic field. This configuration turned out to be perfect for retention of the plasma on the ground.
Behind me is a T10 installation. Frankly speaking, the tokamak itself cannot be properly seen due to the abundance of various wires, light guides and diagnostic systems required to determine parameters of the plasma and perform modern topical research in the field of the plasma physics. As of the moment of its construction, this tokamak was one of the largest in the world. Currently, this is a medium-sized machine, which, however, remains modern and allows us to move towards the controlled thermonuclear fusion.
Regardless of the fact that the T10 tokamak is a massive structure with a height of almost 2 stories, it can be called a full-scale thermonuclear reactor. This is still an experimental installation, albeit with a relatively complicated principle of operation.
Let's consider the main processes that take place here for the achievement of the thermonuclear reaction. First of all, we need a toroidal magnetic field, which is created by the current passing over these coils in order to hold the plasma in the toroidal shape configuration. We also need additional controlling field to maintain stability of the plasma cord. After that, it is necessary, first of all, to create a vacuum in the installation and then supply the working gas. In our case, it will be the mixture of deuterium and tritium. Well, and the moment of truth is about to happen. We've just observed a replica of the thermonuclear reaction.
But how is the mixture of deuterium and tritium heated to such high temperatures that it turns into ionized plasma? In order to carry out a thermonuclear reaction, it is necessary to heat the fuel mix to 90 million degrees Fahrenheit.
We achieved it through using these unique devices, which are called gyrotrons. They are somewhat similar to a microwave oven in principle of operation, but they heat up plasma in the tokamak. The power of each of these devices is about 1 megawatt.
The gyrotron was designed and created by Soviet physicists back in the 1960s at the Research Radiophysical Institute in Nizhny Novgorod. After the very first tests of the device, it became clear that it's capable of solving the problem of heating the fuel mixture for thermonuclear fusion very efficiently. As of now, 2/3 of modern thermonuclear installations in the world are using Russian gyrotrons.
Gyrotron is designed for radiation within microwave range. Gyrotron generates electromagnetic waves at a certain frequency, and these electromagnetic waves form a narrowly focused microwave beam, which is a kind of working body for various applications, including plasma heating in thermonuclear fusion installation. As a matter of fact, gyrotron is a relative of microwave oven, its older brother, so to speak. This is because the working range of gyrotrons is wider and the power is higher, but in fact, it is the same vacuum microwave generator as magnetron.
In order to develop 1 megawatt, this is the power of the gyrotron. Several thousand magnetrons are required. Such a high level of performance is ensured by a whole complex of high-tech solutions. For example, in order to emit such a powerful stream of electromagnetic radiation from the gyrotron, the most expensive part of it was designed, the diamond window.
The diamond as a material withstands high temperatures and has a high temperature transmission ratio. That is, one point is heated and the temperature is immediately transmitted to the periphery where the water cooling is used. The diamond withstands the temperature without melting and cracking. This is why it is the only material applicable for use in powerful devices.
The assembly of 1 gyrotron window takes about a month of hard work. This is without considering the 2 months during which the diamond window is actually grown. It's no surprise that the creation of 1 gyrotron takes 1,500 hours of continuous work. Such a long production cycle is explained by the fact that every device is designed individually and absolutely all parts of it are manufactured manually.
Well, the test and training of a gyrotron often take most time. It can take at least several months. Well, and the whole production cycle takes at least half a year.
It's amazing how much effort and time was put into making this possible.
Three, 2, 1, go!
Just like that, simply by pressing a button, scientists from the Kurchatov Institute just launched a thermonuclear reaction. This is an amazing event, but there is no noise, no buzz, no strange smell, or even vibration. It seems that nothing actually happened. But in fact, a real star has just lit up in the depth of the magnetic trap. Ideally, the hydrogen plasma shall be pink. However, depending on which gas is added during the experiments, it can be painted blue, green, or red. The darker the color, the hotter the plasma. However, the main indicator of a successful launch is its uniform glow. Any flashes or sparks indicate the occurrence of a real emergency. For example, there may be foreign particles in the tokamak chamber. However, regardless of the color of plasma, scientists only managed to confine the energy of thermonuclear fusion on a T10 plant for just a second, and this time is not as short as it seems.
It is extremely difficult to achieve these conditions. This is due to the fact that the energy lifetime of the plasma confinement is not very long, and its behavior is very complex and depends on the parameters of the plasma. For many years, we have been trying to achieve the so-called T, which is about 1 second. Little by little, we have come to it.
Tau is one of the variables of the so-called Lawson criteria. It denotes the plasma confinement time in the installation. Another important variable, N, is the density of high-temperature plasma. The Lawson criterion is met only if N multiplied by tau exceeds this value. In its turn, this will mean that the thermonuclear fusion reaction will finally become a source of energy, not just a demonstrative flash of plasma. As of now, the Lawson criterion cannot be met on various installations across the world. With all the success of calculation, an effective thermonuclear reaction is rather a lab success than regularity.
We managed to achieve a nice density, around a unit by 10 to the 14th, but the confinement time of such plasma is extremely low. In other installations, it is possible to confine plasma for quite a long time, but its density is fairly small. On some installations, it's possible to achieve both T and N, but the necessary temperature of the plasma, which is about 10 kiloelectrovolts, cannot be achieved. Therefore, our current task is to combine these three indicators, these components, and meet the Lawson criterion properly.
However, there are certain achievements. For example, the world record in plasma confinement was registered in February 2016 in the Chinese tokamak East. At a temperature of around 90 million degrees Fahrenheit, the scientists managed to maintain the thermonuclear synthesis energy for 102 seconds.
Indeed, the record parameters are currently quite high. But if we express them, for example, in terms of how long a train or a plane could work on this energy, we can see that these values are not that great.
It's been 65 years since thermonuclear fusion was first performed on Earth. However, the attempts to tame the thermonuclear process and make it fully controllable are still unsuccessful. One of the reasons why scientists keep failing is the plasma itself.
Plasma doesn't behave like a liquid, a solid substance, or a gas. Its behavior is completely different. Plasma is something that is characterized by extremely complex laws, and this something is incredibly difficult to control or confine.
New, unpredictable processes keep happening in the heated mix of deuterium and tritium, which alter the course of the reaction and raise new questions for scientists.
This seems very easy. This is because all the isotopes of hydrogen contained there are all in the gaseous state. They are all ionized, and the electrons are detached from the nuclei. But their amount is so great that fluctuations lead to formations of currents, and the currents lead to formation of fields. All this, through inverse connections, leads to a very complex behavior of the substance. As of now, we don't have an actual proper theory that would help us determine the exact behavior of plasma inside such an installation.
Experimental research is the only way to study the behavior of the plasma. This is the reason why scientists have been lighting discharges with thermonuclear plasma for over 40 years in the T10 installation, sometimes 30 times per day. Understanding the laws by which it can survive on Earth is a fundamental task. From our next film, you will find out how scientists are solving it and in what century our dreams of an inexhaustible source of energy will come true. Imagine the future in which you can afford as much warmth and heat as you want. The future where you don't need to buy energy-saving bulbs, turn off all light sources before leaving your apartment, and worry about large bills for electricity. Now imagine there is only one step that separates us from this future. We just need to learn to control thermonuclear fusion, the nuclear reaction that is capable of providing us with an inexhaustible source of energy for thousands of years.
In fact, thermonuclear fusion is an inexhaustible source of energy for mankind, because it's fueled not by some oil or uranium, the reserves of which are limited in the Earth's crust. Instead, it is fueled by deuterium, which is virtually unlimited in the ocean, and by tritium, which the humanity can obtain from other elements that are also sufficient in number. These elements will provide fuel for thermonuclear stations for an enormous number of years.
Deuterium and tritium are isotopes of hydrogen, the first and the lightest chemical element. When heated to a temperature of 90 million degrees Fahrenheit or higher, they will transform into fully ionized plasma. Due to this effect, the nuclei of deuterium and tritium will accelerate so much that they will overcome Coulomb repulsion forces and merge, forming a neutron and a helium core. As a result of each event of such fusion, 17.6 megaelectron volts of energy will be emitted. The prospects of application of thermonuclear fusion are impressive. First of all, deuterium and tritium, which make up its fuel, are completely accessible. Second, the operation of thermonuclear reactors poses a significantly smaller environmental threat than nuclear stations. There is no problem of nuclear waste. But the most important thing is, the energy generated as a result of the fusion is much greater than the energy from any source known to us.
If we compare a thermonuclear reactor and a nuclear one in terms of the energy generated, 1 pound of the source mixture will produce 3 times more energy in the thermonuclear reactor than in the nuclear one. That is, this device would be much more effective if we compare it to other sources of energy production. Following example may be interesting. 3 ounces of the deuterium-tritium mix generate the same amount of energy as combustion of 1,000 tons of coal.
If scientists are aware of all advantages of thermonuclear fusion, why is there still not a single thermonuclear station? It turned out that gaining control over thermonuclear reactions is an extremely complicated task. It took scientists 10 years just to design the first experimental reactor. A special vessel had to be invented and created to confine the incredibly hot plasma. Famous Soviet scientists Andrei Sakharov and Igor Tamm were the first to cope with this task. They suggested the idea of magnetic plasma confinement in 1950. The first experimental installation in the world, known as a tokamak, was built in the Kurchatov Institute. The design of this toroidal chamber with magnetic coils proved to be so successful that a real tokamak boom occurred. As of now, over 300 such reactors have been built around the world. However, neither tokamaks nor other types of reactors managed to solve the main problem, gain complete control over the behavior of plasma. But why did it turn out to be so unruly and unpredictable? What is plasma actually?
Plasma is an ionized gas. It is considered the fourth state of a substance. In addition to liquids, solids, and gases, there is also plasma, a substance that has been heated to an extremely high temperature. Its molecules are falling apart to atoms, and atoms are ionized, and the substance turns into something that is very difficult to keep at rest.
On Earth, in natural conditions, plasma can only be found in the form of electric discharges of a lightning or aurora borealis. In space, on the contrary, it's literally everywhere. The vast majority of matter in the outer space is in the state of plasma. This includes not just all stars, but also the interstellar medium and galactic nebulae. On the one hand, scientists managed to study well the processes that occur in the space plasma. Astrophysics has been engaged in it for quite a long time. On the other hand, it turned out that the accumulated knowledge is insufficient to understand the laws governing the lives of the stars that light up on Earth.
In this case, we create an object for research by ourselves. The physics of the processes is similar to what is happening on the Sun. However, there are inevitable nuances that complicate it all.
Scientists are still not sure about how the particles and heat are exactly transmitted within plasma. How is energy retained in it in the first place? There is no comprehensive scientific theory that would explain all the processes going on in this mysterious substance.
Plasma is indeed a very unpredictable entity. It constantly brings new discoveries and new surprises that can be either positive or negative for us.
Due to the fact that the behavior of plasma cannot currently be controlled by scientists, the release of energy during thermonuclear fusion turns out to be unstable and non-uniform. This leads to a whole string of additional problems. One of the main problems is associated with the destruction of the first reactor wall. In the tokamak, even such material as tungsten, which is the most refractory metal on Earth, cannot withstand the load created by plasma streams.
If during the experiments that we conduct on the T10, the electrons begin to behave in the wrong manner, accelerate, run away, or accidentally come in contact with the tungsten wall, the wall melts in a single second.
Although this event looks very impressive, it inevitably leads to plasma disruption and termination of the thermonuclear reaction. Every such disruption can potentially result in several months of downtime for the tokamak, but in order to receive energy from thermonuclear fusion on an industrial scale, the reactor has to operate in the uninterrupted mode. It's no surprise that the search for the material that would protect the walls from destruction has become one of the most burning tasks that the scientists are facing today.
One of the most promising ways now is to use some light element. Today we use lithium to build a renewable wall. That is, a liquid, constantly renewing lithium wall. Such experiments are being conducted all over the world now.
Another problem that emerged very recently and became totally unexpected for scientists is common dust. It turned out that it's accumulated directly inside the vacuum chamber of the tokamak. The larger the reactor, the more dust there is. According to the calculations of the scientists, there may be several hundred pounds in the biggest installations.
Every speck of dust has its own area. It turns out that if there is a lot of dust, this dust is not exactly favorable from the point of view of tokamak, as it absorbs, for example, hydrogen in the form of deuterium and tritium, which is very important for the tokamak. Let's say this dust will absorb tritium, and we won't have enough of it. For example, we observe such problems with the Tora Supra installation. When we tried to achieve an extremely long discharge, it turned out that the gas had gone somewhere. But now it is considered that the gas went into the dust. This dust problem is very serious. It emerged very recently.
Heating and confining high-temperature plasma is still one of the most complicated tasks that science is facing now. Scientists all over the world have been trying to solve this problem for over 65 years. Attempts to solve it include various means and construction of all types of reactors. For example, the Stellarator Wendelstein 7X. The construction of elements of this installation began as early as in 1998. In order to assemble all its essential components, the team of almost 500 scientists worked for 7 years. Also, the construction work is still in progress. The first tests of heating and confinement of plasma were conducted in this experimental reactor in 2015.
Currently, we are installing the passive diverter and other intrachamber elements. In order to begin the second phase of operation in the summer of 2017, with 20-fold increase in power and pulse extension to 1 minute, the installation will reach its operational parameters in 2020, when it will be possible to launch plasma with a duration of up to 30 minutes and energy parameters of up to 600 megajoules.
The name Stellarator originates from the Latin word stella, which stands for star. This is because the temperature reached inside this reactor is comparable to the temperature of the sun's core. The design of the first Stellarator was created and engineered by American physicist Lyman Spitzer in 1951. This reactor employs the same principle as the tokamak, the invention of Soviet scientists. It is the same closed magnetic trap for plasma confinement. The difference is that the magnetic field in the Stellarator is created by external electromagnets. Due to its configuration, a Stellarator is considered a very reliable and stable installation.
Unlike tokamak, which still operates in the impulse mode due to constantly happening plasma disruptions, Stellarator is a stationary machine due to its nature. That is, if the Stellarator configuration is implemented, it can work in virtually stationary mode, without disruptions.
Wendelstein 7X is installed in the Max Planck Institute of Plasma Physics in the small German town of Greifswald. As of now, it is the biggest and the most modern stellarator in the world. The diameter of its central part is 17.5 yards. This is not taken into account all the peripheral systems surrounding the reactor. The total weight of the installation is 725 tons. But even if this huge machine will help scientists advance in the understanding of the processes occurring in plasma, Wendelstein 7X is not destined to become a running thermonuclear reactor. However weird this may seem, it is too small for that.
Unfortunately, in order to achieve the reactor parameters, it is necessary to enlarge the plant 4 times. But while engineers can do that, physicists aren't sure whether they are able to predict all plasma parameters as necessary. Therefore, now there is a discussion going on about building an intermediate Stellarator installation, which will be 3 times higher than our machine, and ensure actual nuclear possesses on it.
Moreover, a stellarator has its disadvantages. Its operation hasn't been studied properly. Its design turned out to be so complex that scientists weren't even able to build it for a long time. The existing level of technology prevented them from doing it. There is no surprise that the study of stellarators was abandoned, while the operation of tokamaks didn't stop for a second.
Tokamak is just winning the competition. No one excludes the possibility of a breakthrough in stellarators. But as of now, tokamak is the obvious and undisputed winner of the race.
This is why the tokamak was selected as the basis for construction of the biggest experimental thermonuclear reactor in the history of mankind. It was named ITER, Latin for way, and is now being built literally by the whole world. This is because ITER is the greatest international project. 35 countries of the world participate in its creation. By the way, the idea to unite efforts of different states in an attempt to tame thermonuclear fusion belongs to Russian scientist Yevgeny Velikhov.
Generally speaking, around 1975, it became clear that a single country is hardly capable of it, and that solving this problem wouldn't be expedient for a single country. Therefore, in November 1975, if I'm not mistaken, we offered the Americans and Europeans to work together for the first time.
Various platforms were suggested for the accommodation of the giant reactor in Canada, Japan, and Spain, but in the end, it was decided to start the construction of the century. That's what scientists call it, in the south of France, in Cadarache. The construction of ITER began in 2007 and will continue up to 2022.
Well, there were various discussions, but in the end, it was decided to do it in Europe. In this sense, France has a great nuclear potential. In fact, France has the highest number of nuclear stations in the world. It receives almost 80% from them. The culture and the level of French nuclear power industry and Avera are great, high and obvious, and the nuclear science is well developed. As of now, this is the largest research installation in the world. It cost about 5 times more than the famous ITER accumulator, the Large Hadron Collider. Mankind hasn't built anything like this before.
So what will the biggest experimental thermonuclear reactor in the world look like? According to calculations, it will weigh as much as 3 Eiffel Towers, 23,000 tons. The diameter of ITER will reach 22 yards and its height about 66 yards. The volume of the plasma that scientists are planning to produce in this grandiose plant is estimated as 1,010 cubic yards, which is 10 times more than in the currently largest tokamak jet. The thermonuclear reaction itself in the bowels of this giant will occur at incredible temperatures, 270 million degrees Fahrenheit.
It is now supposed that the first plasma will be generated at ITER in 2025. In 2025, its full-scale operation will begin. That is, with all heating sources and with the deuterium-tritium mixture, the thermonuclear fuel.
In order to confine such a colossal volume of plasma, the magnetic field in the tokamak has to be very large. At ITER, it will be approximately 200 times larger than the magnetic field of the Earth. These values will be achieved through the use of superconductors, several hundred tons of superconductors.
Normally, superconductivity is used to create large magnetic fields because superconductors ensure greater density of the current, and the losses are eliminated as a result. Accordingly, you can create compact magnetic systems that don't consume as much energy as the corresponding copper electrical magnets would consume, for example.
A superconductor is an extremely sophisticated cable product based on niobium titanium and niobium tin alloys. This cable is literally wound on the inner walls of the tokamak to create a powerful magnetic field.
This is a piece of cable for the toroidal magnet of the ITER tokamak. This piece of cable, which is only a yard long, weighs about 33 pounds. It consists of approximately 1,100 niobium tin wires, and it carries a current in the field of 12 T, a current of 70 kiloamperes. What are its main features? It contains many wires twisted into subcables. There is a cooling channel in the middle and a shell on the outside. This is a steel shell, the so-called conduit. You can see the approximate winding diameter by the bent shape of this piece.
Whatever innovative technologies and colossal resources are used for the construction of ITER, this reactor will become just the first step into the thermonuclear future. It is mostly created to study the behavior of unruly plasma at extremely high nuclear temperatures. And only if the heating and confinement tests are successful, the scientists will begin the construction of the first demonstration reactor. It is not expected to happen until 2030.
Such installation is the so-called demo generation. It shall demonstrate to the whole world that all the technological complex of thermonuclear reactor up to the pickup of energy, of electrical energy, can be realized and implemented. How long will a demo discharge last? It's hard to say at the moment, but we're already speaking of weeks, of course. It is not 1,000 seconds, as it is in ITER. It has to last for weeks. After that, the first experimental station needs to be built.
However, no one can predict how it will turn out in reality, and this is not just because there is a whole string of serious problems in the field of thermonuclear fusion. Many scientists believe that mankind won't need thermonuclear power industry in this century at all. But why?
We have the nuclear power industry that occupies a large place. At the same time, we have to understand that with extinction, so to say, of hydrocarbon power industry, whether it will occur in 50 years or in 10 years, we will have no alternative but nuclear power industry. This is because it is provided with fuel, intellectual, engineering, machine and technological resources. It is developed to the point where we easily build stations and make them safe, and so on.
The operation of each nuclear reactor is designed for 80 to 100 years. The problem is that the fuel for the operation of the reactors is the rare isotope, uranium-235, and its reserves are hardly sufficient to provide mankind with energy for the next few centuries. Scientists believe the upcoming crisis of the nuclear power industry can be avoided with the help of thermonuclear fusion, however strange it seems. The thermonuclear reaction is what allows us to generate more available fuel, uranium-233, producing it from thorium, a heavy, low radioactive metal. The natural reserves of this chemical element are virtually unlimited limited. Large amounts of thorium are contained in the granite layers of the Earth's crust. The full cycle of production of uranium-233 to the point of production of the nuclear energy will be ensured by the so-called hybrid reactor. According to scientists, it will combine two installations at once, a nuclear reactor and a tokamak.
What do we have in thermonuclear fusion? First of all, a huge number of quick neutrons with mega electrovolt energy is emitted from this donut, from toroid. The energy is about mega electrovolt. The number of these neutrons is really huge, and this is, in fact, the only thing that ensures this fusion. In a regular nuclear plant, a regular station, there are a few neutrons, and we resort to multiple tricks to make them. Therefore, what can we do? First, imagine that you have a tokamak that emits neutrons. You somehow manage to create a regular reactor that generates electrical energy around this tokamak. For example, a liquid salt one, and the number of neutrons will increase greatly. It will be a hybrid reactor, and its efficiency will be improved greatly.
The advantage of this technology consists in the fact that our current knowledge of thermonuclear fusion will be absolutely sufficient to launch a hybrid reactor successfully. This means that the construction can be started in the near future.
From my point of view, the relatively close urgent step is not the thermonuclear power industry, which has been spoken about a lot recently, but hybrid power industry. Moreover, it is relatively pure from the environmental point of view. There are no shards, since the operation principle is different. This is my answer.
According to many researchers, hybrid reactors will help mankind avoid the energy crisis. Even if the reserves of coal, gas, and oil will run out faster than expected, we will be able to provide ourselves with warmth and light. And scientists believe that the dream of building thermonuclear power stations and finding an inexhaustible source of energy will inevitably come true. The only question is, who will live to see it? Us, our children, or just our grandchildren?